many processors, they have their own their own registers for SIMD. Typically, you've got, say, between 2 to 4 layers of cache. Some cores can have a privileged access to part of the cache. One obstacle that a processor might face is the inability to predict the future, to do speculative execution. So an example of that is a branch that is very difficult to predict. So if this is true, do this. If not, do this.
Hello everyone, my name is Łukasz and this is the Game Engineering Podcast. This time I'm joined by Daniel Lemire, Professor of Computer Science at the Université du Québec in Canada. He's a world-class expert on CPU performance and author of countless open-source libraries, including probably the most performing JSON parsing library called SIMD JSON. We talk about CPU architecture and how to make your programs run blazingly fast. Enjoy! Can you tell me what CPU is doing in a computer?
So, yeah. So, of course, we could talk about what a CPU does for many hours. So maybe it's interesting to take to go back in time. So when I started programming, I started programming on a TRS-80. So it's called color computer because you could do color on it. And at the time, it was very common for kids to program in assembler. We would actually, if you talk with people who are my age, it was fairly common to buy an assembler and start programming with it. And the way it worked, computers back then worked in a relatively and processors work in a relatively simple manner. So you had the list of instructions, and the processor would go one instruction at a time, as you could imagine. And everything was pretty well synchronized. So, for example, if you had a load instruction, it would simply go get the memory, and it would come back. And the architecture was therefore quite simple, and it wasn't very mysterious. Things work, and you could pretty much, just look at the number of instructions, and it would be a good measure of how fast things could go. Modern processors are vastly more complicated. And I don't think we can take them apart entirely, but we can talk about specific topics, right? So usually most programmers, the way they write their code. So let's say the simplest case would be you write your code in C or in C++. You compile it. It generates a bunch of instructions which you can look at. These instructions are converted in binary form, and they're shipped to the CPU. The CPU receives loads this. It's memory as any memory, and needs to decode the instruction. So that's one component of the CPU. It has to have an instruction decoder, and so you have, at this point, you have different choices that were made. So, for example, the x64 processors that we use, so Intel and AMD, they use a somewhat complicated encoding of the instructions. In that, if you just look at the instruction dump, it looks like 1, 2, 3, you've got a bunch of instructions. But if you were to convert them into binary, you would see that it's variable length. So some instructions can be quite long and others quite short, right? So, And so this means that decoding is a fairly complex task. Now, if you have a RISC-V processor, which most people don't, but it's an open source design, it's a little bit popular for hobbyists, and then you've got a very fixed budget of a number of bits, and so it's fairly easy to decode. It's a simple matter. Now, the way the processor works, so it decodes instruction, not all of them, but it decodes them as needed. And very often in a computer, we have loops. I mean, a lot of the time spent in a computer is spent doing loops, and so basically, it's very useful on x64 processors to have a cache, so where the decoded instruction lives, so you don't have to decode them all the time. Now, the instruction decoding used to be a significant part of the processor, but now our processors have become significantly larger, um, in terms of number of transistors. So now you've got billions um, of processors. And so the part that has to do with decoding is now significantly um, less less important. And this plays a role in the sense that um, one of the arguments that, for example, the ARM people would use would say, well, our instructions are easier to decode, so we've got an advantage, but it's a little bit less so now. So that's one part. And then, of course, what the processor does is it tries to um, then it has to operate on the data. Now, the data can be um, either typically there are two main parts where it can be. So it can be in memory, or it can be in register. Now, most of the time, if you're looking at the assembly instructions, people will tell you something like, well, you've got 16 registers, right? So they can be labeled from 0 to 16 or something like that. And that may have been true a while back, but these are actually named registers. They're named, but you actually have inside. If you look at inside the processors, you have many more registers for and I may come back at that, but you've got many registers, many more than say 16 on a x64 processor from Intel. You've got a bunch of those, and so the registers, they're usually like 64 bits on 64-bit processors. So that's the general purpose registers, and they're used for everything. So whether you represent a Boolean or a 30-bit integer or whatever, they're usually used for that. And you've got also flags that are used for signaling like overflow or comparison results. And so you've got the name part. So you've got what you see as a programmer. If you go down to assembly now, most people don't go to assembly, but if you were to go to assembly, you've got this name part. But the processor is much more optimized underneath, and it's got there's just not one flag. There are many, and so forth. So they're quite complex. Now that's one component. So you've got the registers, and which are sort of like a memory, and then you've got the actual what we consider the memory per se, which then is very much layered these days. So you've got typically you've got say between 2 to 4 layers of cache, um, and and so that's memory that's directly fused with the or very near to processor, and it's very fast, and usually it goes into so the closest memory is small in volume, so it's like an onion. So the fast memory is very close to the processor, but it's relatively limited in volume. And then you've got larger and larger amounts of memory. And each time you go up a layer, you get a drastic increase in volume, but also a drastic reduction of performance. So it becomes, so basically the latency, the time it takes for the instructions to retrieve the data becomes greater and greater. And then after that, after you've gone past the memory cache, you've got the RAM itself, or even the disk and the network and so forth. But just the RAM is, seeing it can be much, much, much larger, and is probably going to get larger over time, because now everyone wants to run large language models on their processor. So we're going to need much, much more RAM.
And these
Yeah.
caches are L1, L2, L3. It's usually numbered, right?
Yeah. But this is, importantly, this is not. So if you're always working, say, with Intel processors, it might be like L1, L2, L3. But it can vary depending on the architecture, and it can change at any time. So it's not really possible. For example, it would be totally possible for Intel to, or I don't own any stock in Intel, but let's take Intel as an example. So it would be totally possible for them to have L1, L2, L3, or L4, and say if they want L5, that could be totally possible, and you could not complain if they did that. They can also reduce it. So sometimes you've got fewer um, fewer layers, and mostly this act as a cage. So when you're loading data, it populates these levels, and usually, you know, the memory you've recently accessed is closer to CPU, and the memory you've not recently accessed is further. And eventually, if you don't access it anymore, it eventually leaves the cache, and then you no longer have a copy of it locally. Now, more complicated than that is the fact that our processor, our CPUs are now made of several processors. So they have, which we call cores, and the number of cores can go, there are, except maybe in embedded systems, you usually always have several cores per processors these days. And so can be like 4, 8, and can go up, to like 32, 64, and so forth. But the cache itself, it can be either specific to the core, to the processor, or it could be shared. So, for example, the gamers that buy AMD processors, so AMD makes processors that are very popular among gamers, that have a large amount um, of last level, so typically L3 cache. So they have megabytes and megabytes of cache there. But this cache is usually shared between all processors, not necessarily symmetrically. So part of it could be some cores can have a privileged access to part of the cache, right? And have slower access to other part of it. It also works this way with memory. So when you have several processors, part of your RAM can be more directly connected to some cores and further away from other cores. So it gets complicated. And the reason why, and nowadays we always have cache, and it's taken for granted. But if you go back into past, when I was telling you that at an old PRS 80 computers, we did not have cache. And basically, the instruction would immediately return with memory. Now what happens is that we have significantly, so our clock frequencies got much higher. So I used to program on computers that had, a few megahertz, the clock. So let me backtrack here. So the processor, there are weird processors that don't work that way, but most processors that we use today are in a clock clock regime. So basically, every few billions of times per second, there's there's a virtual click that goes on, and all instructions on the processor are timed, and so they must start always with on this clock thing. And this got very much faster. So we went from megahertz to gigahertz. But meanwhile, the memory, the memory did not, the access to memory did not get as fast as that. So it's not possible within a clock cycle, within this really short time, to grab to memory and continue with it. So if you want to access memory from RAM, it can take thousands of CPU cycles. So obviously this creates a bottleneck. So the processors have different options. So one option, this is just one of the solution they found, was to have this cache memory that serves as, basically, if you frequently access it, then at least it's going to stay locally. You're going to accelerate somewhat the processing. So you're going to still have to wait, but less so than and it was further away. Now, that's one way to speed things up. And a way to speed things up is to make the processors, even just one processor, has a lot of parallelism. So processors, and so having several cores is one way where you can have parallelism. That is, you can do several things at once. And it's quite obvious why, because if a CPU has several cores, then each core is like a small processors that can act independently, even though it shares some memory and other resources, but it's fairly autonomous. But even this one processor has a lot of parallelism built in, and one of the way that's parallelism is that it can do several memory requests at a time, both to the cache but also to the RAM. So so that's how we fought against. So the latency did not shrink. So what we did, we tried to build a cache to get the memory bit to some of the memory to get to remain closed. So this onion layer approach, but also we parallelized the load. So your processor can, so recent processors can issue like 3 loads per cycle. But after it has issued 3 loads, so it requests 3 loads, the next cycle can issue 3 more loads, and it can take quite a while before these loads are satisfied. So it can issue a lot of loads. So there's 2 strategies to try to, and there are other strategies also that I can discuss later on how we try to um, fight the latency from the memory. Now this parallelism is important because it's a fundamental issue on modern day the processors, is that they're super scalar, which means that they can issue several instructions at once. Now, initially, this was like, maybe 2 instructions if you're lucky. Now, increasingly, because we've hit a limit, a physical limit where we cannot accelerate the clock cycle further, what CPU vendors have found useful was to issue So it's to increase the parallelism in terms of the number of instructions that you can issue per cycle. And this has sometimes stagnated somewhat. So there was an era where we seemed it was difficult to write software that would, in practice, retire more than, say, 2 instructions per cycle. But in the last 10 years, this has increased dramatically. And for example, on an Apple makes good processors, and on its Apple processors, it's fairly easy to write real life software where you can retire 4, 6, 7 instructions per cycle. So there's a lot of parallelism built in, and this parallelism is part of the reason why I was making a distinction between named registers and just the true number of registers. This is partly the reasons that you you're working, you can issue several instructions can be issued or completed at any given cycle, and this requires a lot of register space, right? Now, so you've got this kind of I would say horizontal parallelism within the number of instructions, but you've got also a vertical one, in the sense that our processors, to fulfill the goal of issuing lots of instructions, they pipeline the instructions, so they lay them out in a sequence, and they try to predict. So they do speculative execution. So they try to predict the future, and they lay out the instructions. They plan out the instructions that they're going to execute, and so they try really hard to maximize this level of parallelism with disability. And so this is really important for programmers to understand this aspect, because you can look at 2 pieces of code, and they can be and one can be dramatically slower than the other one, even though they look the same at the glance. And the reason why one might be slower is because it faces some obstacles that modern day processors are unable to beat. So one obstacle that a processor might face is the inability to predict the future, to do speculative execution. So an example of that is a branch that is very difficult to predict. So if this is true, do this; if not, do this. If this happens and your compiler actually produced the branch into code, because sometimes what looks like an if then is not actually compiled as a branch, because optimizing compilers try to avoid branches or difficult to predict branches when you can. If you've got a branch and the processor is not unable to predict it, well, what it will do, it will still try to predict it. And if it gets it wrong, then it has to flush everything it was doing and roll back to work and restart. So this is a terrible penalty that has gotten worse over time. So to combat this, what CPU vendors do is that they have immensely powerful branch predictors, which is an important part of modern day CPUs that we did not have many years ago. And they're getting extremely smart. So, for example, basically, if you've got a loop, and within the loop you've got lots of branching, and you repeat always, and it's always the same branches. But let's say you've got like 2,000 of them. Now the processor is smart enough that it can actually learn thousands of branches if they're always the same. If they're changing randomly, then you're dead. It's going to you're going to have a huge penalty.
Is it
But
statistics? Is it statistics? Like what's the most probable branch, or how does it work?
so they use so the early approaches were basically just um relatively simple statistics, which would be um so the simplest thing would be to see a pattern. Let's say, for example, I've got true, true, false, true, true, false, true, true, false, and then I ask you the next one. Is fairly easy, right? Now, this was actually implemented early on, but now we're way, way beyond that. Now they claim to use like machine learning and everything. Like they're far more sophisticated, and they actually have layers of of branch predictors. So they've got more expensive ones, but that they take longer to kick in, and they've got really naive ones that if you have no information, they try their best to guess, but they're not very smart. So this is a competitive um this is a competitive point in the sense that um if you're like AMD and you want to beat Intel, you're going to try to have a better branch predictor, right? Because if you do have a better branch predictor, you're going to beat the other guy. Now, this is very important to understand for programmers, um, because you're basically your processor is kind of like an AI. Uh, it's literally an AI. Uh, that is, it learns, right? And so this means that you can write really. But so we're in CPU, not benchmarking. But let's say you want to benchmark when the effect um, that these branch predictors have and their importance on performance is that if you write, you see that very often people write a very silly benchmark where they have a little bit of data and they do a loop over it, and then they measure the time elapse, and then they say, oh, if I change that, it's faster. But this can be highly misleading because if your actual software does not run the same function with the same input all the time, if there's hard to predict branches in there in your actual code and your benchmark does not reflect that, then your optimization, the optimization you've kicked in, might actually make things slower, and you actually see that. So that's really important to understand that um, your processor is not so predictable. So that's at the level um of branch prediction, but it also works with cage, because we talked about the cage briefly, but one thing to understand is that as a programmer, you have really, really little control over the cage, right? So if you're programming in like C sharp or it doesn't matter, or even in C or even in assembly, or you cannot typically you cannot tell the processor, well, okay, so I've got this table of data here, please put it in L1, fastest cage possible. You have no control of that, and it can actually change. So you can re-execute the same code, and maybe for all sort of complicated reason, maybe the data won't be put at the same place. And this is especially true if you go to a different computer, a different processor. Then the branch predictor can be drastically different, and the page algorithm could be totally different, right? And you have no control of that. In fact, you barely have any visibility at all, right? And so this makes it, a little bit tricky to work. But this is critically important. Um,
We can linger a little bit on this. So what would be the good way to benchmark the code and CPU?
so So this is a very tricky thing. Um, Benchmarking is remarkably difficult. So it's basically what I do almost every week on my blog, but it's it's uh, it's very difficult. So there are many layers to benchmarking, right? So you have what someone might consider like true benchmarking, right? So you've got say you're I don't write video games, so let's say you're a video game designer. Well, obviously, you can measure the number of frame per second as a reference, and the higher the better is fairly clear, right? So if you've got say a web service, you might measure in the real world how many underload, how many requests per second you manage to serve. So this is real world. So the term benchmark, if unqualified, very often will mean that. The problem with this is the end product. This is what you usually want to improve. So if you're making a video game, you want it to run at I don't know 120 something frame per second, or if your TV supports that. But that's what you'd like. Um, the problem with measuring that is that very often it doesn't tell you much about what's going on. It just, like, let's say it's slow. You say it's slow. Fine. What do you do, right? And then so maybe your boss is calling you and say, "Well, make it faster." What does that mean, right? So there was an interesting anecdote is fairly recently, like a few weeks ago. Um, so there's a very important system that people use to write website. It's called Node.js. It allows you to run JavaScript onto server. Now, someone reported that whenever you would on a Mac platform, just on a Mac platform, when you would start Node.js, there was a significant delay of the order of several milliseconds. So a millisecond is 1,000th of a second, but a millisecond is important. Like, this is a huge number in software, and it would get worse over time. So you would add milliseconds, and like, so you had 10, and you had 20, and then 30, and then and it was getting huge. Okay, so what do you do? Okay, so you can measure it. Fine. So what you do, you try different versions. You can try different script that you're on, but all you see is it gets slower. So that doesn't that gives you this can allow you to um have real data that you can make use of, but it doesn't really help you find the problem. In that case, the problem was basically that uh that the code was using late binding. So when you would start to program, it would take do symbol resolution at runtime, and it would tie to, say, for example, tie to function to function declaration to its function um, definition. It would do it at runtime, and of course this means a lot of patching basically in memory, and usually this is very fast. But if you've got a program that's very large, and this is terrible startup time, and so the solution was just to cut this late binding and bind everything at compile time. But finding this out is very difficult. So, and there's a lot of examples like that. And also, the other problem you kind of have is that as you're programming, say you write a function, and then you look at it and you say, well, maybe this other version would be faster. It's not always practical to say, okay, well, I'm going to take my my function, say I've optimized this, and then let's say you're making a video game. I'm going to change my function. I'm going to recompile my game and relaunch it, and then measure the number of frames per second. If you try to do that, what you might see is, well, I don't know. Did it help? Did it not help? It's hard. It could be really, really tricky to know, right? So you won't know. So if you're really serious about performance, what you're going to do is you're going to design what we call micro benchmarks. So the idea is you try to isolate the issue. So you have, it's more like, so benchmarking in general is more like engineering. So but micro benchmarking is closer to science. So you say, okay, I could code this in 3 different ways, say. And so you implement them, and then you try to find a use case where you know a kind of synthetic use case. Well, it could use actual data, but you try to build a synthetic use case for it, and try to make it realistic. And if you've learned from what I said previously, if there are branches involved, you make it large enough. So you don't say, for example, you don't sort. So let's say it's a sorting problem. You don't sort the same array again and again and again. You try to sort different arrays, because otherwise, the processor may very well learn to sort your array, and then will give you unless your actual game or application sorts always the same. It would be weird if it were sorting always the same. So it probably doesn't. So you want to design your benchmark, and then you narrow it down. And then what's really tricky here is that you would think, okay, so I'm going to just say measure the time elapse, and this will allow me to decide. But then there are lots of things that are complicated there. One of the problem is that very often, the time follows a statistical distribution. Very often, it's a log normal distribution. So it looks, so there's a minimum. Usually, if you have a given function and you run it on some data, it cannot go to 0. Unless you hit a bug, your function will take some time to do its work. And there's some conditions, according to Cage and branch prediction and the state of everything, there's kind of like a minimum, the best you can get, but this best usually is improbable, so it's not the most common case. And usually it's kind of unbounded, right? So let's say you had a video game and you run it several times through a scene, and you measure, okay, what is the best frame per second I can get? There's probably a maximum that you can reach, that you can measure. So if you run it several times, you'll see at some point it never goes higher than that, for sure. Now, the other way is not bounded usually. So it could be you're really unlucky. It happens that it has to load from disk or whatever, or something happens, or it gets an interrupt or whatever, and then you've got a big delay. Now, if you're lucky, this big delay is very unlikely, very, very unlikely. So what happens? You've got a distribution where it goes almost to, it can be a long time, but but there's this limit to how short it can be, and it kind of looks like this. So there's a bump near the minimum, and then there's a slow slope. Now, the reason why this is important is that this makes it very tricky to measure, because if you have something like a bell curve, so a normal distribution, now statisticians will tell you it's very easy to compute the mean of it's very easy to compute the mean of normal distribution. In fact, pretty much all you have to do is generate several values and take the average, And this will converge pretty quickly to the true average. Now, that doesn't work usually in software. So if you try it and you say, oh, okay, I get a measure. Now I'm going to get 1 million measure. And then I'm going to know the exact average, or that it doesn't quite work. It's tricky, right? So usually you don't need the time is difficult to measure this. You never measure it exactly because it's, as I was telling you about, you have to understand, like, this is not like the good old days where you can measure accurately. Now today you don't know exactly how long things, it's more like a statistical question. So it's tricky to measure. And then you've got other problems. A lot of things can make a significant difference. So of course, the type of processor. So if you switch to processor, something that was faster becomes slower, and vice versa. It's tricky. And the exact compiler and the flags matter as well. So this is tricky. And so another approach you can do to help you, because measuring the time is difficult. What you can do, and what I encourage people do if they can, is to use performance counters. So today, most computers, almost all processors, have performance counters. What these do, so they can do many things, but they always allow you to compute the number of cycles. They always allow you to compute the number of instructions that were usually retired, but retired means it has completed. Um, uh, it usually allows you to compute the number of branches, either total number of branches and branches that weren't predicted. Usually allows you to compute things like how many loads and so forth. And and so instead of just the time, you can sort of get a map of all of these characteristics. And they're very useful because whereas the time it can be tricky to measure, the number of instructions is typically much more stable. So basically, if you were statistically, the number of instructions would be almost always the same. The reason for that is that there are really few things that can change the number of instructions that a function take to execute. Basically, that's through like branch predictions. But if it always follows the same path, then it's going to require always the same number of instructions. Now, of course, I'm not talking about multi-threaded stuff and so on, but the number of instructions can be, and the number of instructions is usually a good bet. So if you reduce the number of instructions that your function takes, sometimes, but not always, it's going to be a faster function.
Why not always?
Well, okay, so going back to what I was saying about what can defeat modern computers. One thing that can defeat modern computers is our critical data dependencies. So here's an example. Suppose we've got an array, and I'm going to write two functions. One is the opposite of the other. So one of the function, I just compute the successive differences. So kind of like the derivative if you've ever done calculus, right? So I compute differences between two values. So index 1 minus index 0, index 2 minus index 1, and so forth, right? That's really easy. Now, what's the opposite of that? The opposite of that is what we call the perfect sum. You just add back the values, right? So you start with the first value, you add the difference, you get back the second value, and so forth, right? What I just said is trivial, but it could be confusing. But if you sit down with a pen, you'll see what it is. Now, they basically generate the same number of instructions, more or less. Yeah, it's very similar, but one is much faster than the other one. So the one where you compute the differences is much faster because basically you can compute the differences in parallel. You don't need to, you can be computing the differences at the end of the array, and at the beginning it's easily parallelizable. And so your processor is going, your superscalar processor is going to like that a lot. Going to go and it's going to line up all of the subtraction, and it's going to execute them at high speed, no problem. Now the problem with the reverse is that you before you do like the fourth sum, you have to do the previous one. So it's constantly stalling, waiting for the previous one.
Yeah.
Right? It's constantly stalling, and so these so you can take an algorithm and you can change it very often to remove these critical paths. It can become faster. So you make sure that this part of your computation does not depend on the previous part, because when you do that, it can be, you can rewrite it in this way and it looks like it's using fewer instructions, but it can be slower. But now these critical path things are not super common. So usually reducing the number of instructions is not too bad. But like a super famous one where you have this critical path is the naive linked list. So the naive linked list, where you've linked list is just basically you've got a node and it's connected to next one with a pointer and so forth. Now, if you want to go from this one and follow it 10 steps, then it's just stuck because it has to load the next node and then the next one and so forth. And every time it has to wait. And this makes it very, very, very slow to do. So so a long linked list that you have to traverse are a terrible idea. So yeah, but as a heuristic, if you simplify the code and you generate fewer instructions, which does not mean, by the way, it's not the same thing as, say, you coding in C# and you shorten your C#, say, and you say, well, I've got fewer instructions. No, you may actually have more, so
Yeah.
it's to actually look at what it looks like when once it's compiled. And unfortunately, tooling makes this difficult very often. So if you're programming in C#, for example, and you want to say, okay, I've got my function, what's the assembly of this function? It's doable. I mean, there are tools there's a plugin for Visual Studio and so forth that does it, but it's it's a little bit tricky, and the debugger can tell you, you can browse through it, but it's often not direct, so um uh and it's also made difficult because in real life the problem is that just looking at the assembly code, it's like looking at spaghetti. You don't know
Yeah.
what you're looking at. It's too hard to read. So if you have objective measures, you say, well, okay, um, my function takes 1,000 instructions, and this guy wrote a function that uses 200 instructions. Usually the 200 instruction is going to be you know faster, and so then you can have some confidence that's going to be that's going to be better. um
Okay. Okay. Can you break down a little bit the topic of SIMD and vectorization of the programs?
okay, so SIMD, it's a nice follow-up on, so I was telling you that our processors are much more parallel than they were. So there's memory level parallelism I told you about, so you can load many things at once. There's superscalar execution, where you can actually execute several instructions at once. And of course, before that, we talked about the fact that a CPU has several cores, and each core acts more or less independently. And now, a really, really, really important part of this has been the addition of SIMD instructions to our cores. Now, pretty much all processors that most people program for have SIMD instructions. So this goes back to, well, the concept I'll define SIMD later, but I just want to give a historical perspective. So, it used to be like something fancy for supercomputers, but basically, since the Pentium 4, which was a long time ago, irrespective of how old you are, it's Pentium 4, like, when is that? Well, it's since basically the beginning of 64-bit Intel and AMD processors. So it's a long time ago. Since this step, they've had fairly good SIMD instructions. So what are those? So the idea is here, okay, it's all nice to be able to issue several instructions at once per cycle, but as I pointed out, it's complicated to get right. And the problem is to align really nicely for it to work out. And sometimes it might not work out super well, and you'll face obstacles. So the insight here is that why not design instructions that can effectively combine several instructions at once. So the idea is that, for example, you've got, so this happens a lot in computer games. For example, you can have 4 values, and you need to add them with 4 other values, right? Now you can do, okay, I'll do one add, one add, one add, and one add, and so I've got four additions. And yeah, okay, so some mini processors can do that these days, 4 for addition in one cycle. Um, but why not combine them? So I have one instructions that can take 4 integers and add them with 4 other integers, and well, I've got 4 sums at once. And why stop there? Why not go to 8, 16, 64? Well, that's what they do, right? So you can do operation like that at once. And that's basically the gist of SIMD instructions. It's basically the ability to do to operate on several values at once with one instruction. So SIMD means single instruction, multiple data, which is a fancy term, but you've got one instruction and you've got several pieces of data, right? That's kind of what they're saying. Now, for that to work, what the way processors work is that they include dedicated registers. So earlier I was talking about general purpose registers, which are usually 64 bits, but can be used for smaller amounts of value. Now, and what they do, they typically many processors, they have their own registers for SIMD instructions, and very often there's this kind of a trick that they use. They share, so these same registers are used for floating point values and also for SIMD, because for historical reasons, right? So the early processors did not have support for floating point values, so pi and so forth. And so when they added this, they needed new registers, and at the same time they were thinking about building SIMD registers. So they very often combined the two. So the same register that can be used for floating point values is typically used for SIMD as well, right? So they're and it's a little bit like the general purpose register, which can be used for like integers of different types, Boolean, and so forth, uh, or for like character values, like um, the 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 SIMD registers are used for more than one purpose, um, and so and so and so these SIMD so you have different processors that design um, different different instructions sets. So you've got x64, so Intel and AMD. Um, they've got layers upon layers upon layers of instruction sets. So it starts with SSC, 64-bit, and then SSC2, and goes on and on. There's a long list. And goes to AVX, AVX2, and then the latest kid was AVX 512, which is very, very large. It's a very, in fact, it's a family of instruction sets. And then it got really, really messy because um, uh, Intel put it on laptops and then removed it from laptops at some point. So it's very difficult to know where it's supported and where it's not. AMD is more consistent, so they from Zen 4 onward they support AVX 512. So you can sort of expect next generation consoles if they're made with AMD processor. Expect Sony and Microsoft probably to go there. They'll probably support AVX 512, whereas say the current generation is more like AVX2. Now these are technical terms. It's not clear what they mean, but basically AVX 512 is a very rich set of instructions. Now, the 512, what it means formally, it means 512 bits, meaning that the registers can use 64 bytes, right? So they're very wide, but that's not the exciting part. It's the power. Well, this is already phenomenal because it means that you can modify 64 bytes. So let's say you've got a string of 64, you can modify it with one instruction. So that's kind of fantastic, and of course it's really, really powerful. But that's not the most exciting thing. The most exciting things are the crazy instructions that it allows you to do. So one of the insane things that it allows you to do, for example, is you can take 64 bytes and you can um, reorder them as you want with more or less one instruction. So you can shuffle them. It has to
Okay.
be pre-computed, but you can shuffle them with one instruction like that, right? This is amazing. You can you can compact them, so you can remove values that you don't like based on the mask that can be provided at dynamically. So it can just do boom. And so it can do all sort of really, really fantastic things. But unfortunately it's not supported on um Intel laptops. So that sounds great. On the other on the other side of the coin, you've got ARM processors. So if you've got Nintendo Switch, it's ARM, your phone, your tablet. This is
MacBook.
called MacBook, so my MacBook and so on. And these support Neon. So it's usually that's they're different names. It's very different names, but I'd like to call them Neon. So Neon is And the ARM also has other instruction sets, but they're less relevant to programmers. Like they have SVE and SVE2, which are supposed to be like more advanced Neon, but it's not very relevant because it's not very well deployed. But you've got Neon instructions, so they're kind of like the x64 one, so Intel and AMD, but not really. So there are really, really important differences. Well, really important differences. And in some sense, it's more powerful. So the Neon, they have shorter registers, so they're only 16 bytes. So unlike Intel, they don't have 32 bytes and 64 bytes registers. They have shorter registers, but they have really nice and fairly powerful instructions. And importantly, also, historically, now this is changing, but historically, the x64 people, the way it works typically is that you could issue at most three or retire at most three instructions, SIMD instruction per cycle, right? So it was a little bit the limit, whereas you could do many more regular instructions.
Okay.
So this was a little bit of a limit. And when they got, so you have less superscalarity, so you can do fewer instructions at a time, whereas a lot of ARM processors can go to 4. So you can issue more Neon. So you've got very often shorter registers, but you can issue more instructions. So basically, it's less powerful, but not as bad as it seems. So whereas most modern Intel processors can at least do 32 bytes, they have a registers that span 32 bytes. A lot of times they're limited to like 3 instructions per cycle, which is fairly limited. And if you go to 512 bits, so AVX 512, very often you're limited to 2, which
Okay.
is you can issue fewer instructions. So you sacrifice this dispersed color parallelism for more powerful instructions. But still, on the whole interrace, the clear winner, the most powerful in the instructions are AVX 512. They're really, 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 really incredibly powerful. Um, they're really advanced. And if you look at an Intel server chip where they have AVX 512, you'll see that a sizable fraction of the processor is dedicated to AVX 512. So this is not a trivial feature of your processor. The SIMD part can be large. In fact, I was very surprised when I saw that. So it was unclear whether AMD, there's a kind of a race between AMD and Intel, and I actually did not think that AMD would adopt IVX 512 the way they did, because I thought it was very expensive, for them to compete, and I thought it would just drop it and not go there, especially with Intel not being very well engaged with it, dropping it from some of their processors. But it turned out they did a really, really great job, and so this means paradox now is that you know um, these AMD chips kind of really have some of the most. So I've got a gaming laptop with Windows on it, and it's got a Zen 4, an AMD Zen 4 processor, and it's basically best SIMD performance you can get. So this is a feature of the processor. Now, if you want, we can talk about how you program for it, which is
Yes, I wanted to ask about that because, like we mentioned, cache, and you kind of, as a programmer, need to hope that you aligned your, things properly and like they fit in cache. You kind of like you don't have direct control over it. But regarding SIMD, you need to actually do a lot of work in understanding how to use
right.
it. And so let's talk about like programmers' view on the SIMD.
So here there's an interesting component to this. So our processors have a lot of very, very specialized and powerful instructions that if you know they exist, if you know they exist, you can call on them and they can be very useful, right? So for example, without talking about SIMD, I just want to set the stage. So let's say we've got 64-bit integer, and you view it as a 64 bits, and you want to count the number of set bits, right? So so this is useful for, I don't want to say why, but this is useful for for important application. Now, a long time ago, when I started programming, this was actually an expensive operation. You would go and test every bit and do the sum. It's terrible. Now, almost all commodity processors have a really fast instruction for it. ARM has extensions, and even if you don't have an extension, there are tricks. But in fact, it's gotten incredibly fast. Like an AMD processor can do some of all of those at per cycle. Now, the way this works typically is that if you just try to do it naively, right, the compiler might be smart enough. It might try to guess to understand what you're doing and replace it with this fast instruction. But very often what you're going to do, you're going to go to so if you program in C#, I don't have the C# documentation in front of me, but programming in C#, there's going to be somewhere in the standard library a function that does that for you, that say, well, it sums the bits in a word, right? And then the C# compiler will know at some point to turn it into a fast instruction. And if you're programming in C++, not the latest version of C++ standard, and introduce a special function for this. So you've got this mixed thing where you can hope that the compiler recognizes your code and turns it into a fast instruction, which definitely works some of the time. You can use the standard library of your programming language, whether doesn't matter which one it is, Java or C# or C++ or whatever. You can, and this usually works very well. Or you can use like a special library that that you're relying on a library that some expert has provided to you, and you're counting on the fact that it does these things well. So for example, if you're doing crypto in your application, probably won't do, like, you won't write your code, you won't call the standard library, you just probably call a higher level function, and underneath it's going to call some the right instruction. Now with SIMD, it's kind of the same. So you can just write your code as usual and hope that the compiler is smart enough to just do its thing. So that's called auto-vectorization. Typically, there are other names, but that's it. You can use higher level libraries that can help you, or you can use facilities that are provided by your programming language and its standard library. About 20 years ago, the bet was on, largely, a lot of people were betting on auto-vectorization to be the solution. So basically, they said, well, people are not going to change the code, but the compilers, they're going to get much smarter. And it's true that the compilers today are much better than they were. Like the code optimization is much better. But largely, the auto-vectorization has proven to be, I would not say it's a failure, because sometimes sometimes it works well, really well. So if you have a simple case, right? So if you have a simple case, you have two arrays, and you want to add, one array, the values from one array to the other array, and you just write your code, whether it really doesn't matter much in which programming language, almost doesn't matter. Then if you've got a very fast, a very good optimizing compiler, and this include like Java, C Sharp, so it's not strictly limited to low level programming languages. It will do its thing under some conditions. So sometimes it will fail because it's unsure whether it can do it, but very often it will work in simple cases. Um, but it's not very reliable. So that's why, for example, the C Sharp people have done a lot of hard work, and Unity did the same and so forth. They've done a lot of work to bring up these instructions so you can use them deliberately. So you can say, I know I want to use SIMD for this code because it actually matters for me. So I'll do the effort and I'll figure it out and I'll code it myself, even though it's painful. Um, and no, but the reason why this is made possible is not because people are stupid and they do hard work because they should just wait for the compiler to do its thing. It's because the compiler does not do it in a lot of cases. Now, there are various reasons why the compiler cannot do it. Um, one of them is the mismatch between our programming languages and these instructions. They're not the way we code, the way like Java, C Sharp, and so forth are designed. They were not designed with SIMD in mind. And so there's kind of like a mismatch, right? So sometimes it's difficult for the compiler to do the conversion. It's not really direct. Um, and that's a little bit of a problem. It's fairly limited. So you have to sort of do it. So the best results you're going to get is very often is if you're you designing your code deliberately for it. But then there are different levels. So you can use a fairly high level. You can use fairly high level code. Sometimes this high level code will be agnostic to. So it will not require that you know about the instruction sets that you're targeting. So maybe it will work well on ARM, and let's say it will work well on your PlayStation and on your Nintendo Switch. It doesn't require you to bother about it. Can be like higher level. The danger with sometimes if it's too high level. So an example is the Java as a Java vector API. The problem is that to use it well is difficult, and sometimes you rewrite your code using their high level API, but you won't see the performance benefits. In fact, it's possible that you may end up with slow code, relatively speaking. And that's just one example, but it happens in a lot of cases. So that's a terrible outcome because you started with your regular code that you know how to write, and then you did all this work to convert it using some
Yeah.
high library, and then your code is no faster. But then maybe you spend like a day coding, and then you benchmark, and it's no faster. And then what are you going to do? Well, from an engineering point of view, the only solution is to take the SIMD code you wrote and throw it away, because you're not going to, because it's more complicated. Fewer people can read it, and if it's not faster, then out it goes. There's no purpose for it. So, but sometimes it works. Sometimes, depending on your application, it can work very well. So, for example, cases where this works, if you take your browser, so there are basically only two browsers, more or less, these days, or
Yeah.
Okay, you got Firefox, which is in big trouble. So let's put aside. But basically, you've got WebKit, Safari on Apple platforms, and then you've got Chromium, just like Chrome and Chrome and Edge and Brave and all
Yeah.
these guys. And basically, these are two main browsers, browser engines, and they both use SIMD. So, but they don't do it low level. They do it using they do it using relatively high level software libraries. So the Google folks use Highway, which is a Google um, it's a Google library that does SIMD for you, and
Okay.
so it's a little bit easier to use. So you don't it's higher level. And the WebKit people use something called SIMD Everywhere, which is again the same idea. And as the name suggests, you just write from one platform and then tries to find the best equivalent everywhere. So these are two options, right? And clearly they work well because the browser people they don't write SIMD code. They don't put SIMD code in it if it doesn't help because
Okay.
so this can work in a lot of cases, and but then you've got the other option, which is where you write really specialized code, and possibly you say, okay, I'm going to write my Neon code. So let's say I want it to run fast on my iPhone, let's say, and so you write specialized code for this, and then you say, well, okay, there might be parts that would work well on both, say, my PlayStation and my iPhone, but I'm going to write two functions and optimize them separately. So and then you go lower level where you try to really use your knowledge of the instructions because they do different things and there are different strategies that are, some are best there, some are best elsewhere. Now, this level needs quite a bit of knowledge, and relatively few people get there because, well, there's only so many hours in a day. So this is much more demanding, but this is where you can get some magic happening. So you can get like performance that is totally insane, and that looks like magic because nobody can achieve these kind of speeds, without knowing really, really well the processor work. And basically this requires, a lot of knowledge because you have to know not only which instructions exist, you have to know like the patterns, how to use them. Because if I give you a list of instructions, how do you solve problems? You need some patterns in your head. I can put this and this and solve this. And also you need to know how fast they run, which is not easy because Apple will not tell you. So it will sell you an iPhone, but it will tell you, oh, okay, yeah, we have, yeah, we support this instruction because it's there, but it won't tell you how fast it is. So, 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 so this is, and actually this is true certainly for x64 also, like AMD and Intel. They all have like optimization manuals, but a lot of the information is incomplete and so forth. So you got to reverse engineering to do some reverse engineering on it, and the information is like not very well available. Um,
When you're talking about this level, this like lower level now, you mean
mhm,
specific instructions for specific processor? So,
yeah,
for example, doing intrinsics. Like, I
yeah,
know what instruction I want to use. I don't want to write, for example, C code now. I want to write the name for the instruction for the processor to use.
yeah. Well, typically you can go. So if you're like if you want to do SIMD programming in like Go, the Go programming
Yeah.
language, then you'll definitely go to assembly, and then you'll link your assembly with and then there are like software libraries like you know OpenSSL, for example, that we use, for crypto stuff, then they'll definitely do that. But most people will not go down to. That's not what I mean. You typically will not go down to this level. So usually, so if you're programming like in C or C++, you'll have you use the word. You'll have intrinsic functions. So these are like regular functions, except that they're the the compiler knows about them, so they're not generic function. They're functions that the compiler knows when it sees this, it needs to. Well, the compiler system as a whole, not so it's a complicated discussion, but basically the way the compiler system is made, if you see this, then it knows exactly how to translate it. Sometimes, fairly often, it translates it to one specific instruction. Not always, but very often that's how it's going to go. So basically, you're writing in C, but it's not just C or C++. So this same approach works in Rust, Swift, the Apple programming language. It works in C Sharp very well. So C Sharp, they've done a lot of work. You can even call like crazy AVX 512 instructions in C Sharp, and actually C Sharp, like I'm referring to like .NET, but there are different, like Unity has its own support for, you know, for people who are game programmer. Unity has its own support for SIMD instructions as well, which tells you kind of why it's fairly important. So this low level programming is fairly important because a lot of people actually invested a lot of work into making it available. The problem, so there are good chances that if you're programming in C, C++, Rust, C Sharp, and there are other programming languages, like I'm just not, you can enumerate them. Well, not like JavaScript and Python, but you know, but these languages, like, they support that, and there are a lot of people who've invested a lot of time in making it work, and because this is hard work. And so this tells you that it does bring substantial benefit, because this is so much hard work that Microsoft would not do that if it didn't make a difference, right? So the engineers there, they're not going to waste 3 years of their lives coding this stuff if it doesn't work. And it's actually, so it's kind of like very specialized skill, because as I was saying, even if you, like, let's say you're in C Sharp and you say, okay, I know exactly which instructions I want this and this and this. C Sharp will do it for you, but you still have to have the knowledge, and they will not train. Well, they will not train you for free. They probably won't train you at all. So you sort of have to learn it on your own, kind of, or find someone who will teach it to you. But this is not, very well covered. I don't know, where people go to school these days, but most schools won't cover this
Yeah.
because.
Do you have any pointers for this? For, like, you notice that, like, in order to program in SIMD, you need these patterns, right? It's not about, like, learning the instruction this, instruction that, but more of a pattern, how to lay out and think about the problem. Do you have any, like, tutorials or things to point to learn this?
I did not prepare a list. There definitely, like, there are people who have prepared courses. Um, um, uh,
We can
I,
list them. We can list them in the description if
yeah.
you send me afterwards.
But for tomorrow, but the difficulty is that um it's the same as, okay. So the reason why it's not so simple, it's a little bit like learning. At some point, you learn to program, right? So I don't know how you learn to program, but I'm a computer science professor, and what I tell students that are learning to program and they really dislike my answer is that you're not going to learn to program by reading books or watching videos. I mean, you're sure your videos are great, but if someone never programs and watches your videos,
Yeah.
they're just not going to learn to program. I mean, they may think they learn to program, but they won't. That's not how it works, right? It's like when to learn a language, like say English. At some point I had to learn English. Um, you just don't learn English by listening to people, you know, uh, uh, talking English. That doesn't work. Yeah, at some point you have to talk in English, and then you find out. So that's also a big problem. So I know people who've taught themselves, well, we've all taught ourselves at some point, SIMD programming. And basically, the way it works is you say, the way I would suggest people do it, and I'm not saying you shouldn't buy a book or watch videos and so forth, but the way I suggest doing it is that, okay, I've got this project and I want to do this part using SIMD. And okay, let me try to do it. Now, we have one tool today that we did not have many years ago, and there are large language models, right? So large language model may help you actually. So, um, so you say, okay, I've got that, but you have to start simple because you have to understand what you're doing, right? So you say, I've got this function. Can I rewrite it with simply intrinsic? And large language model will kind of, well, if you use them, you kind of like copilots and so forth. It will sort of do something, will be slightly wrong, but you'll learn, you'll figure it out. The difficulty is that this approach works only partially because the problem is that you also at some point you have to design if you want to max out the performance. At some point you need to design the algorithm um, in terms of SIMD, and you cannot start with the code. So you have to you actually at some point at the advanced level, you actually have to think about it because it's not, it becomes. But to get started, in 2025, I would definitely consider using large language models. Something like Copilot, or I don't want to advertise for Microsoft. Doesn't matter which tool you but some one of those tools, right? You know what I'm
Yeah.
talking about. They can help you do, and I would just do like simple things. And if you want to do it like you can pick which options you like. Like for example, you could say, okay, well, I would prefer to write kind of like instruction set agnostic code, and let's say I'm using C++. So then you could say, okay, I will use um, uh, you know Google Highway, or SIMD everywhere, and and defensively, like these large language models will help you, you know, code using these things, and that could be an approach. Or you can say, well, no, I want to go crazy, and I want to target like arm neon, and I want to do this, and that could help you get started.
Okay. Okay. Have you taken a look at Mojo?
Yeah, actually.
So, as far as I understand, you can add like type annotations that would be SIMD related and then have some sort of performance benefits from that, right? Is this
Right.
correct or?
Yeah. Yeah. So even at a meeting with Chris on this, but where basically the intention of Mojo is um so I don't know if the people watching this know what Mojo is.
That's true. That's true. I should think about it before. But yeah, let's do a bit of an overview what Mojo is, and then we can talk
Yeah,
about specifically.
yeah. So the idea is that arguably the most popular programming language today is probably Python, right? you know, it could be JavaScript maybe or TypeScript, but Python has become very, very popular because of data processing, um, AI, and all of these things, right? So the problem with Python is that, well, it's not really a problem. Python is a great thing, right? The great thing about Python is that you can write your C code and you can hook it up with Python, and it's a little bit painful, but not that much. And then you can get this really, really powerful code that runs under Python. So PyTorch, for example, is an example for people doing AI, where you can, NumPy, and there's a lot of powerful libraries like this. The problem is that the Python code itself is super slow. It's like 1,000 times slower than C, and 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 so you're always limited by in what you can do. You're always limited by what the library underneath does, because if you start writing too much Python, it will get really, really slow. So the trick with Python is to write relatively little code and rely on libraries to do the number crunching underneath, right? So you start having a bunch of loops and so forth. Then you say, no, I'm using PyTorch, but I want to do something that they've not expected. And so I want to write my own loops and everything. Then it's going to be dead slow. So that's not good. So the idea with Mojo is to design a programming language that is very much Python-like, um, but compiles down to basically compiles down to something as fast as C or something. Ultimately, that might be the goal. So so the guy behind it is Chris Ladner, who's famous because he sort of started out LLVM, which is one of the main compiler backend. It's used by a bunch of programming language like C, C++, and when you compile Clang, it's even hooked up in Visual Studio. You can compile with LLVM as a front end inside of Visual Studio. I think other programming languages use LLVM. And so he's really and he designed Swift, the Apple programming languages. So he's not very lazy. And
That's to say
so,
the least, yeah.
yeah. So now he started this business where basically you've got Mojo. And Mojo, the idea is that it's more or less like Python, but it's Python where you can program, like you're programming in Python, but um, you're basically getting the speed of like C at the level. And so it's a little bit so they do want to integrate they are integrating SIMD programming into the programming language. It's still Mojo is not exactly like complete. It's not complete yet. So if you're a game programmer, I don't think you should launch your AAA engine in Mojo. That's probably too early, right? Uh, um, but yeah. So they want to try to um they want to try to solve many of the problems that we're facing when doing SIMD programming. How well they'll succeed, like history will tell. So one of the one of the pain point that I raised with Mojo people, but that, that you're always facing is, okay, so when you're programming and you say, I'm going to use these fancy instructions, now it works on your computer, that's great. But of course, the user might have a different computer. So that's that's a little bit of a problem when you're targeting a specific instruction that is not always available, right? So that's a very vexing problem. So basically, the .NET people solves it is they say you can put a branch. You can say, well, if I have support for ARM Neon, do the following. If not, do the following. So you can have these branch, and that works well um, because well, I mean, it's more complicated than that, but basically it works well because .NET is um, usually relies on JIT, so it compiles, at runtime, and so it compiles on the machine that people is running, so the machine knows which
Yeah.
instruction. So that's not a problem. But if you're coding like a game in C++, for example, that's a little bit trickier. That's a little bit trickier because then you're compiling it once on your machine, but then you don't know. So these are like fun problems. Now they have solutions, right? But the different solutions, there are many solutions. But basically, what you do is it's the same trick. So you do what they call runtime dispatching. So basically, you have some component of your program. It can be even like if you're compiling with GCC, it will so it has functionality help you with that. You can tag a function. You can say this function should be used when the hardware supports this and that. Otherwise, use this other function. Um, or you can do it by hand. You can say, okay, I'm going to have this function here that's going to check what is supported on the processor, and then I'll redirect you to the right piece of code. So what you can do is what you can do is you can compile different version of your code, and it will pick once when the program starts. It will pick the right one. Now that's the messy part if you're an x64, because x64 has these layers of onions, and it's kind of tricky. Now that's not so much of a problem if you know, for example, you're targeting the PlayStation 5, right? Then you know exactly the processor, and then there's no problem anymore. It's not so much a problem if you're targeting ARM processors, because except for specialized instructions, they pretty much have the same instructions. But for like if you're programming for like PCs, it's very messy. It's very messy because it could be anything, and so you got to plan for everything. And this is a little bit of a challenge. Now that's something like a language like Mojo can solve at at a higher level. That can make it easier on you.
Okay.
Um,
Okay. Somebody asked an interesting question on X. How would you compare SIMD and trying to have your program handling like vectorized code, doing lots of instructions in parallel, and SPMD, so single process multiple data approach, and exchange the data if you need through like ISPC, IPC, inter-process communication. Like what would be how would you view this? Like, can I run the same program as a couple of processes, do some sort of work, and then maybe exchange data compared to running one, but spending a lot more time making sure the intrinsics are in place, for example?
so one of the benefit of SIMD is um, one of the benefit of SIMD is that it tends to be uh, so the irony here. Okay, so SIMD is simple and power efficient compared to most alternatives. This is about the cheapest form for the processor, not for the programmer who has to have headaches. But for the processor, this is about the cheapest form of parallelization there is. That's why it's everywhere on all commodity processor. It's really, 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 really efficient. Now, what you can do, so for example, if you compare SIMD programming with, say, multi-core programming, um, what you're going to do is, with the SIMD programming, say you're going to go like twice as fast, and you're not going to increase significantly, typically, the power usage of your core. It's going to be, SIMD is not much more expensive. Whereas the fellow who is using like multiple cores is going to multiply its power usage. So that's going to be a difference. Also, also the problem you have when you're using, say, multiple processors is, this works very well if you've got a lot of data, but it doesn't work. It has a lot of difficult obstacle, right? So communication is a problem you've got very often. The communication, there's very often a significant latency, right? With which is a problem. So you need to coordinate, which is really, really not free, not at all. It can be very, very tricky. And whereas SIMD, for example, you can communicate between your SIMD instructions and your regular old school instruction. The overhead is very teeny. Like we're talking about, like 3 cycles or something like that. Like you can go from one to the other, like it's a few cycles. It's very, very cheap to move back and forth. So, um, and the other thing I would say is that, like SIMD is a like all of the tricks you can use. They're not really competing against each other per se. They're it's more like they add up, right? So you use different strategies to accelerate your code, um, but it's not usually you don't necessarily say, well, I'm only going to use SIMD, for example. That's ridiculous. So there are cases where SIMD is useful. So you can rewrite part of your program maybe using SIMD, and that's going to be useful, but it may not solve other problems. And you may need other strategies for it. So for example, if you download, there are, if you want, let's say, for example, you wanted to run a large language model on your CPU. So this is a popular thing that people do these days. So of course, the problem there with your CPU is that typically CPUs are access to limited bandwidth. That's it's not the fundamental limitation of CPU, but that's just how most, you're going to have a trouble finding a CPU that has high bandwidth RAM. That's just, some were made, but they're not widely available. So most of us have very limited bandwidth on our CPU. But putting that aside, so let's say if you want to run your large language model on a CPU, what you're going to do is you're going to have multiple threads, and each one of these threads will be using SIMD, and you're going to combine to two to max out your performance. That's how you're going to do it. There's an interesting related issue, which is on our CPU evolve. So in the good old days, um, um, like vendors like Intel, for example, adopted hyper-threading, where your single core could run through threads or four, sometimes. The, the, this was one strategy to beat the limitations that I was outlining earlier, where, say, for example, you have data dependencies and you cannot retire enough instructions, so forth. Your branch is mispredicted and you're stuck. So what you can do is you can try to have several threads per core. And this was largely viewed as the future. So basically, you'd have, a lot of virtual cores, um, and and there's this competition between, and there was also an attempt by Intel. So Intel at some point released night landing processors, which were kind of a little bit like GPU processors. There were a lot of cores, but the cores were tiny. There are some ARM vendors that do that also, like Ampere, as these cells, these CPUs. They're very, very not powerful cores. They're tiny, but there are many of them. And it's kind of this competition between the two, between having, okay, I'm going to have this large core that's very powerful and run just one thread, and it's large, and I have many small ones, right? And I think at some point in the past, the future was viewed as, well, in the future, you're going to have you're going to have a million, or maybe not a million, I don't know what people were thinking, but you're going to have 20,000 cores, but they're all going to be really, really tiny. They're not going to be powerful. And interestingly, that's not, that, that, at least that's not winning very clearly. What we're saying is that we're saying, like, the number of cores on our CPUs is not increasing that fast, and the cores are clearly getting bigger, and hyper-threading is not trending that much. The CPU vendors are not rushing to put more hyper-threading, so to run more threads per core. It seems rather that the opposite is kind of happening. So the big cores, at least on CPUs, appear to be, a winning proposition. And part of that, I think, has to do with the difficulty of having, of taking the workload and dividing it into lots and lots of different threads, and then having to coordinate all that, right? It's kind of like, but basically, if you want to use an image for it, it's the difference. Okay, so you're starting a company. You have the choice between hiring 10 of the very best engineers in the world, or else you can do the same thing, the same money. You're hiring 1,000 programmers, but they're not very good. They're kind of stupid. So which company is going to be more successful, right? So both types of companies exist, and both will be successful. But it seems to me, this is hard to predict the future, so I'm not going to do it. To me, that the small companies with 10 very best engineer, right?
Yeah.
Which is like CPUs with like 10 cores, but they're really, really, really smart cores, is winning over the guys we're just going to max out the core. Now, that's for CPU. Now, if you talk about GPUs, then
Yeah.
it's less clear.
Yeah.
This is
So this is what I wanted to ask as well. So it kind of seems like the CPU design goes this way because you have this counterpart, which is GPU, and all of the tasks that are need to be massively parallelized, but not that, like, I would say, intensive per core, you can dedicate to GPU, right? That's why CPU are specializing on this like couple of cores, but superpowers, and GPUs have like thousands of cores, but less so. Is this the case?
it's always difficult because there's very often when I write about performance on my blog, and I'll say always encourage people to test on their own application. So it's always, so it depends on there's lots of different people that do different things, and so it's really hard to make broad, assertions. So I like to say that it's difficult to reason in the abstract, right? So reasoning in the abstract is like, you go high level and you're saying, well, okay, here's so you've got to be really humble. But what is complicated is, and I alluded to it, is that uh, for all sort of complicated reasons, we don't have CPUs with good bandwidth. Typically, like the CPUs, for all sort of reasons, are bandwidth limited. Now, one exception of that to that is Apple makes some Apple Studio boxes where the processors have a lot more bandwidth than normal PCs, and there's a lot of memory level parallelism and so forth involved, and they were very well designed. And you see people running large language model on these CPUs, which is comparatively more difficult on a lot of PCs, right? So that's one equation you've got which is kind of like totally separate from whether it's a GPU or a CPU in a sense, is that how much parallelism, memory level parallelism do we have? So how much bandwidth do we have? These are really, really, really important questions. And my take is that irrespective of everything else, I think I'm hoping we're going to see a lot more focus on bandwidth. So one of the trends that we've all seen is AMD coming up with these CPUs that have a lot of cache, a lot more. And I think that the vendors will probably find a way to give us more memory bandwidth. So that's one aspect. Regarding the GPUs, it's very complicated because they're actually drastically different GPU design as well. So if you look at Apple designs its GPUs, it's fairly different from NVIDIA the designs their GPUs. So the number of cores is completely, it's not at all related, right? So but clearly, so Apple uses significantly fewer cores, but they get fairly good results nevertheless. So both designs appear to be possible into GPU space. So more and smaller cores or larger cores. But it's clear that for GPU programming, the really small, stupid cores are clearly more of a possibility. They've got more of an edge because the problems are typically more trivially parallelizable, right? So it's easier to do if you're multiplying matrices. It's clearly fairly easy to parallelize. But a lot of programming is not so easily parallelizable. And there was a big trend at some point. People would do things like it was viewed as GPU would be the future, so they would do they would design a database engine on GPU and all sort of things like that. And then they would do these benchmark, GPU against CPU, and we say, well, the GPU is much faster, but very often when you actually look at it closely, you would find that, well, yeah, okay, but you do not make a very good use of the CPU. And if you actually do, you'll find that the CPU, if you actually leverage all the power of your CPU, it can give your GPU a run for its money. So that's why we're not, relatively few people are running MySQL on GPU. This is just not something that's happening, broadly speaking. Um, so so it's difficult to predict where the future will go, but a large trend that's happening that's really clear is what they call dark silicon. So earlier I told you that if you look at at an x64 processor with AVX 512, you'll find that they're spending a lot of silicon on AVX 512. Okay, and if you think about it, that's slightly hard because, okay, so maybe my code does not use VX 512. So what's happening with this? Well, it's underutilized a lot of cases, right? But they don't care that much. They don't care that much if it's underutilized. Um, like a lot of people will buy an Intel processor that has a bundled GPU with it, and they'll never use it because they have a discrete card, right? This is fairly common. So the general trend is that we're accumulating in our systems specialized silicon that is not always being used. This is true everywhere. Your phone has probably processors that you know never get used for sort of reasons, but it's cheaper to just put it there than a specialized the hardware device for so you just put it in every machine. And um and this clearly is the result of the fact that we're getting better at putting many more transistors into small places. Uh, and this trend is probably not going to reverse itself, which means that we're able to put a lot of feature into our processors. If you look historically, you would buy a PC, your CPU would not do that much. Would do like main compute, but um, like you would even have like a math coprocessor that would do the floating point stuff. It wasn't even bundle. Uh, if you wanted to play sound, you'd have like a sound processor. If you have one of those old uh, consoles, that's how it worked. Everything was separate, and
Physics also had its own card, right?
yeah, exactly. So but now we're creating these large systems that have that include everything, including stuff that you'll never ever use, uh, just because it's not that much more expensive because a lot of the money is spent on design, and that's the design is very hard, but production can be streamlined a lot. It's still very expensive, but we have all sort of tricks that they use to make it so clearly what's going to happen is that it's kind of like my analogy with 10 smart guys. It's worse than that. So it's not just that you're going to hire 10 smart guys, but uh, 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 in these smart guys you have or they can be gulls, by the way. That this was not sexist, so I don't it's so a lot of ladies who perhaps this is not, but so you so one of them could play the piano, one of them would be a history buff, one of them would be great at designing graphics and so forth. You hire them, but maybe you don't need graphics because you're doing a back end. That doesn't matter. They're really, really, really super smart. They took a lot of courses in college, right? And they're really, really well trained. And if you need it, you have it. Otherwise, you don't care, right? So, so you really have these big brain people that you hire. This seems to be the direction we're taking. Getting these systems are really, really powerful, and there are big cores and a lot of stuff that we're done using. Now, this being said, maybe I'm totally wrong, and the future could go could go the other way because it's really hard to predict, right? So all I can say is that this gives the impression that this is the trend that we're taking, but you always have to be humble. I remember a few years ago there was an initiative which was works on ARM, and this was before Apple adopted ARM and so forth, and I bought an ARM server. So AMD, the AMD company that makes the processor, they were selling actually ARM processor, ARM server. Yeah, this is a true fact. And so I own one, and I bought these things, and I was making sure to, was trying to learn about ARM, and so forth. And I picked up a tablet, an Apple tablet, which I rooted, and I was using it as a kind of a programming station and so forth. And people thought I was crazy because the idea at the time was that, well, okay, ARM is really nice for these small, low power things, but it's never going to match up Intel. Like the big chips are Intel, and Intel is untouchable. And there was this arrogance, right? So Intel people would say, well, we're the only ones who know how to make big, powerful chips. Um, um, well,
How the tables have turned.
the tables have turned, because now you nobody thinks that, right? So you can for all sorts of reasons. Like if you're playing games on a PC, you're probably still at this day you'll probably go with an x64 processor for all sorts of reason, but it's not because Qualcomm cannot make a good um, CPU that you could use, because they can, right? What's probably stopping you is a bunch of software related issues more than anything else, and it's not a kind of and so we're probably going to get them, a Nintendo Switch 2 later this year. I don't know. Uh, because it's Nintendo, it's probably not going to be very powerful. But but if they wanted to, right? If they wanted to, they could make it a beast. They're not, they're really really powerful chips that you can make with
Yeah,
based chips that you can make today. There's absolutely nothing stopping someone from coming up with a console that could revolve, that could
yeah,
beat
yeah,
the existing. So you have to be humble, because you don't know what's coming. So it's possible, it's not unthinkable that in the near future we could be buying laptops with 1,000 really tiny cores. Um, this could happen, but you'd have to, you have to you have to explain how you solve the problems of coordinating these cores, for example. That's really hard. Like you probably know, like in the gaming industry, uh there are a lot of video games that perform poorly, like they struggle because they have problems with making use of all the available cores, right? This don't scale well with respect with the number of cores, and often this has nothing. These are not idiots. They're not like silly programmers who don't know what they're doing. They're just stuck because there are difficult problems. And very often we're talking about, okay, making good use of like 8 cores, and that's often they cannot do it. It's hard to, like, let's say, double the speed going from 1 to 2 cores, and then doubling to when you go from 2 to 4, and then doubling. Like if that were easy, we would be doing it. But you know, and then give these guys 1,000 cores, and then what's going to happen? They're probably going to give up at some point. They're going to say, well, I can make good use of 10, and I don't know what to do with the 12,
yeah,
with the others,
yeah. Uh, when you take a look at CPU, you can see that the architecture there is quite open compared to the GPU. You, at least in terms of like ISA, you know what kind of instructions happen, and you can like target them directly. Why the world of GPUs is so much more closed?
Well, so part of my explanation earlier was, I think that it's not so incredibly open. So the it's documented, but not all that well. So
Yes.
so for example, if you want to know how the branch predictors work, well, you better do experiments, because they won't tell you, right? I mean, it's on the silicon. So if you've got a microscope, you can maybe study the thing, but they won't tell you. They won't give you much in terms of the algorithm. Um, and as I was saying, you don't really have control of the cache, and they don't give you that much, right? And a lot of it is reverse engineering, right? So we do a lot of reverse engineering to figure things out. Um, of course, the instruction set itself is open. Um, um, uh, they sort of have they don't really have much of a choice, in the sense that none of none, I think, so maybe there's an exception that will prove me wrong, but none of the CPU vendors actually control um the CPU, the compilers. You're like, you're writing your code and you're compiling it with Visual Studio, say. um so Intel has kind of no choice but to give Microsoft. So if they come up with new instructions, they have to provide Microsoft with information. Otherwise, or else is Microsoft going to, use it in their compiler. And it's the same thing with GCC and Clang and so forth, right? So the PlayStation is kind of derivative of FreeBSD. FreeBSD, I think, it uses LLVM. Well, if you come up with a processor and you're not pushing, providing the information to the LLVM, well, you can code it yourself, you can contribute, but by contributing, kind of document how it works, right? You have to document. So we have, for example, an example of that is that because of the sort of commercial war, I'm not getting into politics, but there's a little bit of a commercial war between the Americans and the Chinese, right? With respect to CPUs and so forth. So there's and so the Chinese have started building their own chips. So there's a company, Longsun. I might be mispronouncing, but so they have their own ISA and everything. And they're not documenting it very well, but they had to go to GCC and Clang, probably, and LLVM, and they have to, here are the instructions, and here's how you can compile your code, because it might be doesn't matter whether you're Russian, Chinese, or Hungarian, or African. At some point you're going to use a mainstream compiler to write your code, right? So they could, in theory, write their own secret um, uh, compiler. You can do that. Like, Intel and AMD, I think they have their own specialized compiler, but in case of Intel, at least, they gave up maintaining their own, and they kind of use a LLVM, and it's a variant of it. So that's one angle. Now, if you look at GPU folks, well, typically they've now, again, there might be exceptions and nuances that I'm not getting, but mostly they sort of build their own compiler, so to speak, right? So so um, so NVIDIA, if you want to run code on their GPU, um, they'll basically provide you with the software, CUDA and everything. They'll provide you with the stuff to run, so they don't need someone else to do the low level work. But I'm not sure this is like, so this is there this I'm not sure this is a fundamental difference, because it could have evolved differently. So there, but I would say, if you have if you have kind of like an integration, like like if you're Google or Amazon and you're building your own specialized processors, and you do, by the way, and and it doesn't matter whether it's for like it's GPU, CPU, it doesn't matter too much what it's for. But if you're building your own and you're also providing all of the software stack, the tooling so that people can use it, then you don't really need to document, the details of the inner working, or even the instruction sets, because people don't really need to, you're going to take care of it for them. So why would you pay people to write documentation and maintain the documentation and so forth? It's a lot of hard work, which you don't need to do. Um, so, and that's kind of like the power of, so if you take like ARM, for example, why is it powerful? Is because if you use their instruction set, then your processor will work with GCC, say, like that, or Visual Studio. It doesn't matter. It will work. So for you, it's kind of like saving. But if you're rich and powerful enough that you're willing to write your own compiler and everything, um, and you don't need, open source support, then it's a kind of like a different equation. But I don't see why it's not possible to, um, have a more open GPU ecosystem. That could happen. Um, and certainly, for example, AMD has been more open about it than NVIDIA. But again, that's somewhat because NVIDIA has invested more in providing the tooling, so they need less help from other people, so they can be like, you know, uh, I would not qualify them as secretive. They're
Okay.
it's not, but they can be more locked, a little bit more closed. You know.
Okay. I figured that I did not ask the most important question, so I guess we can close with this one. Provided the architecture you outlined of the CPU, coming back kind of full circle to the start of this discussion, what a programmer can do to leverage the modern CPU architecture to make the program faster. You mentioned a couple of these regarding the branches, but let's say like an overview of the techniques.
Right. Well, so there are different strategies, but to me, it's a little bit like program correctness. So program correctness, what do people should do is invest in a lot of testing, right? That's how you get a good a program to be correct, and you start relatively early on. You don't wait until everything. So I know some people program like this, so they write everything and they throw it into a debugger, and then they spend 6 months debugging it. So so I have this very controversial take where I don't use a debugger because I never need it.
Okay.
And what I do is basically I early on I write a lot of tests, and I test everything from the ground up. And so I never spend a lot. I don't spend a lot of time debugging, honestly. And I've got lots of software that I'm maintaining, and I rarely debug. Usually people report a problem, it's fixed within the hour or so. Uh, Performance is kind of the same. So my philosophy with respect to performance is kind of the same. So you start, and then so a bad strategy is to write whole thing, and then sometimes there's no choice for all sorts of reasons because you don't control everything. But if you write the whole thing, and then afterward you say, okay, let's see how fast it is, you know, then you get something like the catastrophe of CD Project Red, where you come up with a game that will run on the platform you're targeting, and then PlayStation has to pull your game from the Cyberpunk has to pull your game from the. It's fairly embarrassing. So what's happening here is because probably they waited at the end and they say, okay, let's look how fast it is. Okay, it's too slow. Let's make it fast, and then they struggle. So I think a much better strategy is to early on to start benchmarking as soon as you have something, and then measure and measure and measure and measure again. Um, one of the things that people don't do enough is to track the performance over time. So what happens very often is that someone will say, "Oh, I've got a change here. I'm going to move this guy here," and nobody looks at the impact it has on performance. And the worst thing is that sometimes people say, "Oh, I'm going to optimize this," but they don't measure. They say, "Well, clearly it must be faster." And this happens. You can watch me on GitHub very often. This happens, right? Someone will say, "Well, I've optimized this part," and I say, "Okay, did you run a benchmark?" And then sometimes people will go silent, and sometimes they'll just disappear because they never did, right? So measuring, just like testing, I know it's super simple because it looks almost like stupid, right? But people who write fast code, in my experience, they've spent a lot of time benchmarking. Now, just like program correctness, as you train yourself to write more correct code, you need less testing to keep you on track, right? So let's say you've never programmed in C++, it's your first year writing in C++, you're going to do all sorts of silly things, you're going to break things, it will be terrible. So you have to spend to be very, very, very careful. But if you're super experienced, you can go and it won't be so bad, that the code won't have so many bad lines of code. The same is true with performance. If you've trained yourself over 10 years to write really, really efficient code, then you're less likely to do to have terrible blunders. But that it can still happen. So an example that happens, like if you're programming in C++, for example, what happens very often is that it's trivial in C++ almost to make copies without you realizing. This happens all of the time. Okay, so I had a blog post last year about this, or about, like, for example, in Node.js. So we had a problem where basically the way it's architecture, we to have access to a string, we had to copy it, and all the time. But it wasn't apparent in the code. Like, you would think, oh, I'm just getting the string, but you weren't really making copy every time. Now you say, okay, it's copying a string. How bad can it be? Well, I mean, at the margin, it adds up, right? And then it can significantly reduce your speed. So how do you? So at some point, you find out, okay, I can avoid this problem. But this is partly experience, but it's also so one way that helps is diversity. So how did we know, for in the case I gave you, how did we know that Node was not very fast? Because there was another system using exactly the same code that was much faster. So Bun is another JavaScript runtime. Bun was twice as fast. But the difference is Bun was not copying the code. So and I call this the diversity, in the sense that what you do is you compare against your competitors, and very often this is also a very important information. For example, some people say, "Well, I don't need to be fast, to be faster, because my code is probably fast enough," and that's fair. That's fair. But very often, there's an answer they should be able to provide: is how fast could your code be? So you ask me to provide a function, right? And you say, "Well, I wrote this. This is correct, but it's not as fast as it could be." and then but you could turn around and ask me, okay, but if I need it to be fast, how fast could it be? And if you cannot answer this, it's an engineering question that is important, right? Because people sometimes they don't know enough about the software to know how fast things could be, and so sometimes you can. One way to know is to take a competitor and benchmark the competitor against you. Now, if you're, you know, let's say you're 50 times slower than the other guy, so maybe then you should react to. Now, maybe you're only like 30% slower. So maybe that doesn't matter for your application. But usually, you know, um, so measuring helps you a lot. Um, um, and it's the key to engineering because unfortunately people say, well, small differences doesn't matter too much, but these things add up. They do add up. So a critical point in this is that so you have a very good model of software performance, and and people sometimes have bad assumptions. So a bad assumption is, well, okay, most of the code that I write does not need to be fast, and only like 10 lines of code in my whole program matter. And later I can find these 10 lines of code, optimize them, and then my software will be fast. But this is just about as stupid as thinking that, well, most of my code does not need to be correct. I only need these 10 lines of code to be correct. No, because any bug anywhere can make your whole thing fall apart. And it's kind of the same thing with software performance. So you cannot just isolate one thing. You have to think about the whole thing. And so this means that constantly you have to, you should be measuring different part of your software, or at least know how fast they can be and how fast they are. So you know for a fact that this part does not matter. Okay, but if it matters, you know that you can crunch it and make it much faster, and you have an idea of a well to do it. But this requires a lot, because if it were like, if performance were a simple problem where you have one bottleneck, then I could be billionaire, because they could just hire me. I would find out the 10 lines of code, I would optimize them, and nobody would ever have a performance problem anymore. But no, it's super complicated when you get there. Sometimes the entire architecture, is broken. And this is a low performance. I mean, basically, sometimes the only option is you have to throw everything away and start again. And it's the same thing with, how correct the program is. Sometimes if your architecture is wrong, it's always going to be buggy, because it's not architecture the right way. So, but if you're not testing and you're not measuring the performance, you don't know. So one programming language that I kind of wish was slightly more popular is Swift, for example. Another one is Go. Now, what these guys do is that they have test. They support. It's built in. You have support for test, but they also have built-in support for uh, performance testing, right? So you can run your test. You can run your benchmark, right? And so if someone comes up with a change, you can say, "Oh, I'm going to benchmark things. Is this slower or is this faster?" So what you can do is you can continuously monitor the performance of your thing, and if some point it's bad, then you can do like a bug tracing. You can say, well, it got worse. But I would say, like, the way you get really, really fast, it isn't this matter. So a very good example is SIMD JSON, which is arguably maybe the fastest JSON parser in the world. It we wrote, but how did it work? Okay, so we started working with Jeff Langdale, and the first version was not very fast, and then it was actually depressing, but it was it was private. And then we simplify it, we optimize it. And at some point, we were beating what was at the time the state of the art. So we released it. And then what we did is over the years we optimized it. And at some point you reach a point where, the only way to go faster would be to do something different, and which we did, by the way, later. But um but basically you've got this curve here where you go, and it's not like, okay, it's slow and then, oh, I've solved the problem. It's these curves where you go, okay, I've gained 3%. I've gained 3%. And if every week, well, no, but the problem is, if you gain percentages like this, right, you're actually, it's exponential progress. Like, for example, you've got this show. If your number of people, if the number of people watch you increases by 3% each day, this sounds depressing. But if you look at the curve, this is actually, you're headed somewhere, right? Clearly, because you'll be on an exponential growth. So it's kind of the same thing with software. You've got to shave it off continuously, and this looks depressing, and sometimes you'll get lucky, it will go, like that. You'll have fun, but like if you just keep working at it, it will get faster and faster, and then at some point you'll hit diminishing return, right? So but that's one way, like measure, 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 measure all the time.
Okay.
Absolutely.
Okay.
And then you'll just build up competency and so forth. And because there's no, they're good books. So I can they're very good book on software performance, and there certainly talks that you can watch and so forth, and they're useful, but and you should keep them in mind. But it's really practice and practice and practice. That's like, there's nothing else. So and if you cannot practice if you don't measure.
Okay. Okay. How did you get to 100 top contributors to GitHub?
So I'm among, maybe like, it's maybe top 500, I don't know, but so I started using GitHub many years ago, and at some point it was just like, for me it was just convenient, because before that I was using Subversion, and before that CSV on my private server. And when these guys open up, I said, well, this is very convenient, and it's free also, so this fantastic thing, and does a lot of tooling, so I started using it. And then I just, I'm just very engaged in open source, because I can, that's kind of my model, because I'm a university professor. And but one of the way that I like to publish my work is as open source software. This is not typical, and it's not typical at universities, because that's not how professors work typically. But that's a model that I find very, very useful, to just write good software, and put it out there. It's a model that works well, for me at least, because I get feedback. If you write a research paper, nobody reads it. I don't know how many research papers you read per week, but most people do software, they read none. So we were talking about Chris Ladner earlier. I've argued that Chris Ladner should receive the Turing Award, which is kind of Nobel Prize of computer science. But I have no idea how many research papers he has written. He has written some for sure, but my point is, he has produced stuff that's clearly advanced the state of the art, but mostly, not solely, but mostly through open source. He's contributed work, and so that's the model I've used, and this allowed me to get feedback, and including critical feedback. So which helps me do better work, and find problems also. That's really important. Find problems that people care about. And I've just been posting it on GitHub. So I think and then people have decided that maybe it would be cool to follow me to see what I would do next. Uh, but I've not, just to be clear, I've not tried. Like, this is not a plan to. I've just observed at some point. So, oh, okay. So a lot of people follow me, like thousands and thousands of people. I just noticed it. This is just like happened, and I said, oh, okay. This means that they'd like to find out what I'm going to do next. So but this was not intentional. This is not like, you're you start a YouTube channel and you want to grow, and then you find out what strategies you're going to grow. Like, for me, it was just like, I'm going to just put my software out there, and just so happened that people like it, and well, they like some of the software, and but so the other thing that I do that may contribute is that I blog. I've got this blog weekly, which is, so I've got something, and my blog is paired with GitHub. That is, the code is posted. Not all blog posts has code, but a lot of it does, and it's always posted on GitHub. And so this is a tie-in, but this is not a plan. This is like an evil plan where my blog promotes my GitHub account and so forth. It's just but this is something, this is something I do, my blog, just because um so as a professor, to me, this is a way to connect with actual people in the industry, with so I express ideas, and then I get feedback, and people say, oh, well, it's interesting, did you know that? And then they tell me something, and then they say, oh, I did not know that, and then I take notes, and I write things. So yeah, so
Can
I
you
don't have a good answer on how to do it.
can you mention also what kind of projects you contribute to, you created? You mentioned SIMD, JSON, and Node.js, but what about others?
So Node.js, I'm just I contribute a little bit, but it's like there's probably like over 100 people, and this is a very long running so this is not my personal project. I just do stuff in there. My main Okay, so I won't go back like super far into past, because that would be boring. But one of the things that I did is I've been interested in performance for a long time. So I worked on an index format. It's called EWA. You don't need to know, it's EWAH, and this got picked up by Git. So if you're running Git, the main implementation that you find from GitHub uses this index format. After that, one of the things I did, I I started a project called Roaring Bitmaps, which is a follow-up of this, which is basically a way to it's an indexing technique, which is used by a lot of important system, including, like, say, YouTube as a database engine, Priscilla, I think, and they use Roaring Bitmaps. It's using lots of big data system, um, and it's available in different programming languages like Go, Java, C++, and so forth. So that's one characteristic of my work, by the way, is that EWA also was available in different programming languages. So sometimes I like to offer different version of the same idea in different programming languages. So I SIMD, so we got interested in parsing. So this was done with Langdale, Kaiser, and different people. And this is ongoing. So basically, the idea here was to show that JSON could be parsed at gigabytes per second, so really, really fast. So now there are benchmark show that you can do, like, you can get JSON and parse it at like 10 gigabytes per second on one thread on an CPU. I work on a library that I've written at some point. I was frustrated because parsing numbers was slow. So say you have 3.1416, and that's a string. You want to convert it into a number, binary number. This is stupidly slow. And and the only library that was available was written by Gay many years ago, and nobody had revisited it too much. And well, there were a few implementations, but it's very scarce. And so I wrote a better algorithm with collaborators on that. And this is now available on. This is the back end in GCC. The LLVM people are going to implement a version. It's in Go. It's the standard library. It's in the standard library in .NET and so forth, in Rust. So if you're parsing numbers, there are good chances that you're using our algorithm. We wrote a super fast URL parser. So this sounds really stupid because you'd say a URL. How bad can it be to parse a URL? Well, it's super, super complicated. It's amazingly complicated. So we have the fastest. This was with Yagiz Nizipli. Is that called Cloudflare, which you may know. It's a company that does a lot of web stuff. And this is our node, for example, parses URL. So it's a URL parser. The latest thing I'm working on with a lot of people is called SIMD UTF. So SIMD UTF. Okay, so that the floating point stuff that I just mentioned, like this is in the mainstream parsers. No, mainstream browsers. So sorry. So it's in WebKit and Google Chrome and so forth. The latest project that we're working on is in the UTF. This is also in the mainstream browsers. So what this library does, it does transcoding very fast. So in modern day systems, there are two types of string formats. So you can have UTF-16 or UTF-8. Most strings on the internet is in UTF-8, but if you're on the Windows or in JavaScript or in Java or in C#, your strings are typically UTF-16, meaning that each character using 16 bits. Whereas on the internet, typically it uses 8 bits, or if you're coding in C, very often you're using UTF-8. Or ASCII, but ASCII is a special case of UTF-8. So it does conversion very fast. It validates also the inputs. And the latest addition that we added was support for base64. So base64, when you're sending an email and you're attaching a picture or a Word document, the email format does not support binary data. It has to be text, so it converts it to text, and it's like random looking text. Your crypto keys are also usually encoded in base64. You can also embed base64 in your browser as a data URL, so you can hide a picture inside HTML. So for that, we have a really fast routine to encode and decode. So I'm probably forgetting some stuff, but
That's a lot of world-class software.
so you were asking why people follow me on GitHub. Well, the reason might be that I'm working really hard to do I'm not alone, by the way. These all projects with a lot of very smart people. But so I'm working on a lot of stuff and contributing to a lot of different projects. So you mentioned Node, but we've contributed to the .NET Microsoft .NET library. So contribute to different. I've contributed to the C++ standard library under Linux. Trying to contribute here and there when we can. So these all open source contributions and so forth. And really the idea here is, my model is to try to have good ideas, but to also get people to use the good ideas. So you try to develop an algorithm or a method and so forth. You write about it on a blog. You write about it in research papers. You post the code, and then someone says, "Well, okay, I'm programming Go. Your Java software does not help me." You say, "Okay, fine. I'm going to port it to your programming language and so forth." And yeah, if you just for fun, if you go to my GitHub page, you'll see that the number of repositories, and especially if you include the organizations that I'm tied to, is large. So I'm involved
Oh yeah.
in,
Oh yeah.
in a lot of different things.
All right. Daniel, thank you so much for joining me. It was a pleasure. And thank you so much for also your work. It's a stellar work, and you are bringing performance to light for all the people, especially for people who follow you on X. You mention performance a lot, and thank you so much for everything you've done, and thank you so much for this conversation.
Thank you.
Thank you so much for listening to this episode of the Game Engineering Podcast. Don't forget to subscribe on YouTube and follow on Spotify and other podcasting platforms. See you in the next episode.